Hello again. This is your instructor, Jerry Pinter. Welcome back for part 3 of our lectures on motion in one dimension from chapters 1 and 2 in the textbook. In this part of the lecture, we'll talk about the kinematics of falling objects. No discussion of falling objects is complete without mentioning the work of Galileo, the father of modern science. Galileo viewed the understanding of nature based on evidence, experimentation, and observation. He viewed the laws of nature as mathematical. Galileo was able to separate science from philosophy and religion. This was a huge leap in human thought and sparked the beginning of a scientific revolution. Galileo was extremely intelligent and also very resourceful. In fact, he sometimes used his pulse as a clock for experiments involving moving objects, as there were no stopwatches, of course, in his day. Galileo was the first person to use the telescope for astronomy, and his discoveries there were enormous to advance science. He discovered sunspots on the sun. He discovered 4 moons of Jupiter and watched them rotating around Jupiter, proving that not everything revolves around the Earth. And his study of the phases of Venus ended up proving that the sun is the center of the solar system, not the Earth. Eventually, the Catholic Church actually placed Galileo under house arrest until his death for his radical ideas. Galileo did a bunch of experiments involving falling objects, and that's really the key thing for our lecture today. Falling objects are said to be in free fall. That is, they're under the influence of gravity only. One of the key things that Galileo discovered, and he was really the first person to document this, was that all objects, no matter their weight, shape, size, or composition, fall at the same rate. Now, when we say this, we have to be careful to avoid air resistance because that will affect our results. Galileo supposedly did a lot of these experiments by dropping things off of the Leaning Tower of Pisa in Italy. We're going to try to recreate some of experiments. Unfortunately, I have to be in my backyard, not in Italy, but nonetheless, please enjoy the next set of experiments where I will drop various objects of different weight and different size and composition, and notice that they always fall exactly at the same speed and hit the ground at the same time. Our first test is a tennis ball and a 5-pound weight. Our next test is a tennis ball and a 20-pound weight. This test is a 20-pound weight and a light wood block. Hello again. When we do these experiments, we have to be careful about air resistance, also called drag. So let's try doing an experiment here in the garage where there's no wind, and let's drop a heavy book and a coffee filter. What do you predict will happen in this experiment? Here we go. All right, I'm guessing you were right. And the coffee filter, of course, fell very slowly because of wind resistance pushing on it. Can you think of any ways we can reduce the wind resistance? Well, there's a couple things we can do. The first one is we can reduce the surface area of the coffee filter because that's where the air is pushing on it, creating that wind resistance. So if we crumple it up into a tiny little ball, now we have the same weight, but much less area. So we've reduced the wind resistance. So let's redo our experiment now and see what happens. It's going to be a little hard to see the coffee filter now. But as you can see, they both fell at the same time. Now there's one more way that we can reduce the wind resistance. We can place the coffee filter on top of the book, like this. And what that'll do is the book will actually block the wind that's striking the coffee filter to reduce the wind resistance. Let's see what happens here. You can see that the coffee filter dropped just like a lead weight. Thank you. In addition to noticing that all objects fall at the same speed and hit the ground at the same time, Galileo also discovered that all falling objects accelerate while they fall. In other words, they speed up as they fall. Thus, all objects fall with the same so-called acceleration due to gravity, which we will call g for gravity. So if we drop objects here, they are in free fall, and they are going to be accelerating downward to the Earth with an acceleration equal to some number or value called g. We can do a simple experiment to actually estimate the value of g, the acceleration due to gravity. So to start with, let's come up with a formula that will allow us to calculate g. So we can use the position formula from the last lecture. For a free-falling object, all we have to do is note that instead of our object moving along the x-axis like we did in the last part of this video, now objects are going to be falling in the y direction. So we're going to change, this is our position formula from the last part of this video. We're going to change delta x to delta y since we're falling in the y direction. Also, remember this first term is the initial velocity. Well, we're going to drop objects starting from rest. We're going to release them from our hand. So their initial velocity is 0. So this term we can eliminate. The last thing we have to do, we have this term here, 1/2 a delta t squared. Well, the acceleration, we're going to call that g because it's the acceleration due to gravity. So we're going to replace a with g, but we're also going to put a minus sign in there because g actually has a positive value, but g, the acceleration due to gravity, points downward. So we're going to replace this a right here in the formula with negative g. So here's our free fall position formula. The displacement in the y direction is equal to minus 1/2 g times delta t squared. And since we are trying to determine what the value of g is, we're going to solve this equation here for g. So you can just do a couple steps of algebra, and you end up with g is equal to negative 2 times delta y divided by delta t squared. So for our experiment that I'm going to show you next, we're going to drop a ball 2 meters, and we'll use a stopwatch to find the average time and plug those values in here and come up with an estimate for g. So I hope you enjoy the demonstration. Okay, in this experiment, we're going to drop this tennis ball from a position right here marked by this tape that's exactly 2 meters from the ground. And we'll time it, and we'll take a series of measurements here to see how long it takes for the ball to drop. So I've got my stopwatch on my cell phone here. Let's do some experiments here. All right, our first experiment, the result is 0.61 seconds. .66. 0.63. Let's go ahead and come up with our value for g based on our data that we just took, sort of in the spirit of Galileo. We took 3 trials that I showed you, and the times were 0.66, 0.61, and 0.63. So I went ahead and averaged those, and it comes out to be 0.633. So that's our time interval. Also remember that the ball dropped 2 meters, so the displacement of the ball, delta y, is actually negative 2 meters because it's falling down. So what we're going to do is in our formula here from the last slide, we're going to plug in delta y is negative 2, that's right here, and we're going to plug in for delta t, we're going to put in our average time 0.633. When we square that, we get 0.401. And notice up here, we get this minus sign out in front cancels that minus sign. So we just have 2 times 2, which is 4. So on a calculator, this expression here turns out to be 9.97. And remember, this is an acceleration, so the units, which I didn't show here, are actually meters per second squared. So our estimate, if we sort of round this, you can see it's very close to 10 meters per second squared. So that's our estimate. It turns out the actual value of g that we're going to use in this course is 9.8 meters per second squared. So we got very close. Coming up with 10 instead of 9.8 is only a 2% error. So we had 98% accuracy just with this simple experiment that I did in my backyard. Now, making some remarks on the experiment, there are obvious ways we could improve these results and get more accuracy. One of them would be to drop the ball from a higher height. This would allow less error because the times here that I was measuring were less than a second. And so by going to a higher drop and maybe with even a heavier weight that has less effect with wind resistance, we could improve our result there. And then, of course, instead of using a manual stopwatch, relying on our reflexes and our hand-eye coordination and so forth, we would want to use some sort of electronic automatic timing. And if we were to do these two things, we could certainly get closer to this result of 9.8. So in summary, the acceleration due to gravity, if we drop any objects, okay, remember it doesn't matter what they are, as long as there's no wind resistance. This could be a tiny pebble, this could be an automobile. Everything falls exactly the same with the acceleration due to gravity called g, and the value of g is 9.8 meters per second squared. Now, one thing we have to keep in mind is this value here of 9.8, this is only effective here on Earth. Gravity is different in other places in the solar system. For example, on the moon, gravity is about 1/6 as much as it is on Earth, so the value of g is something like 1.6 meters per second squared. On the surface of Jupiter, because of its large mass, gravity is much larger. G is something like 23. And on the sun, again, if the sun had a surface and if we could stand on it without getting burned to a crisp, we would measure the acceleration of gravity on the sun to be something like 274 meters per second squared. So now let's take a look at the equations we can use for objects in free fall. Well, there's some bad news and some good news here. The bad news is there's a whole new set of equations for free-falling objects. In fact, on this page, you can see I've listed 6 more equations for us to use. However, the good news is that these 6 equations are exactly the same 6 equations that we used earlier in this chapter. The only thing we have to do is replace x with y, because we're moving in the y direction, not in the horizontal x direction. And the only other thing we have to do is replace the acceleration a with minus g. And remember, g is 9.8. And once we make those changes, we have a new set of equations that are, basically exactly the same, and they're used to solve problems for objects in free fall. So we have our displacement equation here, our velocity equation. Average velocity is just displacement divided by time. One of the nice things about doing problems with free fall is that the acceleration is always the same. It's minus 9.8 meters per second squared. So we'll never have to calculate the acceleration for an object in free fall. We know its acceleration. It's negative g, which is minus 9.8. We have the velocity equation here. The final velocity is equal to the initial velocity. Before we had plus a delta t, now we have minus g delta t. So again, we've just replaced the a with negative g. And also notice in these equations, there is a subscript of y for the velocities. We see it up here too, v sub y average. This is v sub y f for final. v sub y I for initial. This just reminds us that the velocity is in the y direction and not in the x direction. This is the position formula, right? This is the long formula that we learned about in the last part of this video. For this one now, for free fall, again, we've just replaced all the x's with y's, and here is our acceleration. Now it's negative, notice the minus sign there, negative g. And then finally, this is a very useful formula that we've seen before. This is the final velocity squared is equal to the initial velocity squared minus 2g delta y. This is the equation that's useful when there's no time information involved. So whenever we are solving problems involving free-falling objects, all right, objects moving up or down just under the influence of gravity, we will be using these equations to solve the problems. So next we're going to go ahead and look at some examples of using these equations. Here's our first example of a free fall word problem. Suppose we have a bowling ball that's on the top of this 100-meter tall building, and we push the ball off, and the ball falls and hits the ground below. So we're going to solve three different problems here. Part A is how long does it take for the ball to hit the ground? Part B, how fast is the bowling ball going when it hits the ground? And part C, how far does it fall during the first 2 seconds? So let's go ahead and solve these in order. So for part A, how long does it take the ball to hit the ground? So what I've done here is I'm using the position formula from the last page for a free-falling object. Now, we have to be a little careful here. Remember, the object is starting up here, so its initial position is 100 meters. Okay, so you can see y sub I, that's the initial y position, is 100 meters. The final position over here on the left, y sub f, is 0 because the ball ends up down on the bottom. So you can see we put the 0 there. Since the ball starts from rest, okay, whenever something falls, unless it is thrown with an initial velocity either up or down, if we just drop something or if it just falls, then the initial velocity is always 0. So this term drops out. That's kind of nice. We get a 0 there. The next thing to do, of course, is remember g is always 9.8. We have the 1/2 out in front, and our unknown in this problem is delta t. That's what we're going to solve for. So, we can get rid of all these zeros here, and we can move things around here. We can put this 100 meters over on the other side, and so we end up with this equation here. And finally, to solve for delta t, let's get rid of all the stuff out in front of it. I can multiply everything by 2 to get rid of the 1/2. That's the 2 right here. I can divide by 9.8. You see that down here, and the 100 meters is still up here. And then notice the minus sign here cancels with the minus sign here. So we're just doing a few steps of algebra here to solve for delta t squared. And of course, we want to solve for delta t. So to get rid of the square, we just take the square root of everything on the right side. So we have the square root of 200 over 9.8, which on your calculator you will find to be 4.5 seconds. So that is the free fall time of this bowling ball from a very tall building, right? 100-meter tall building. It takes 4.5 seconds for the bowling ball to hit the ground. Part B of this problem was to find the velocity of the bowling ball when it hits the ground after falling off the 100-meter tall building. There are actually 2 ways to solve this problem, and we're going to see this quite often when we do problems in physics. There's often more than one different strategy to solve the problem, and one is not necessarily better than the other as long as they get the same answer, but sometimes one method is shorter or more efficient than the other. But let me show you both ways we can do this. We can use the equation for the final velocity of a falling object. So again, this equation here in the blue box is shown a couple slides ago on that list of equations. So once again, I would recommend when you're doing problems on the homework or on the quizzes to have all these equations right in front of you so that you can quickly go to them and figure out which equation is applicable and which will be make the most sense to attack the problem. So in this case, we're looking for the final velocity. That's what the problem asked. So we're going to look for an equation where we can calculate the final velocity. And there are actually two of them, but this is the first one that shows up on that list. So the final velocity is equal to the initial velocity minus g times delta t. So remember again, the initial velocity of the bowling ball is 0. That's right here. G, of course, is always 9.8 since we're here on Earth. And delta t, we just found that in part A, that was 4.5 seconds. So the answer is simply 9.8 times 4.5, which is 44.3. And then remember, we have this minus sign out in front. Now, what does that minus sign mean? Well, the velocity is negative 44.3 meters per second. That just reminds us that the ball is falling downwards. The negative sign, remember, tells us the direction of the velocity. Now, the other way we could have solved this problem was by using the formula without time in it. This is the v final squared equals v initial squared minus 2g delta y. So again, the initial velocity is 0, so that's that term right there. We have 2 times g is 9.8, and delta y, remember, that's the displacement of the bowling ball. Now the ball, again, is falling 100 meters downward, so the displacement is negative 100 meters. So our answer for this is, remember, v final squared is equal to 2 times 9.8 times 100, and the minus signs cancel in this case. So that's 1,960. But remember, this is the square of the final velocity. So our answer is the square root of 1,960. And you might remember from math class, when you take a square root, there are two possible answers, a positive and a negative solution. So our answer here mathematically is either plus or minus 44.3 meters per second. But here we can use just some logic. We know the ball is falling downward, so the velocity has to be negative. So again, our answer here is negative 44.3 meters per second, which of course is consistent with what we found up here. Part C of this problem asked, how far does this ball fall during the first 2 seconds? Remember, it takes 4.5 seconds for the ball to fall all the way down to the bottom. So during the first 2 seconds, of course, it's only fallen part way down. So here we can use the position formula for falling objects. Again, this is one of those formulas on that sheet from a couple slides ago. So our final position is equal to our initial position plus initial velocity times delta t minus 1/2 g delta t squared. So let's fill in what we know here. Well, remember our initial velocity is 0. Okay, so, and then, I'm sorry, that's over here. Our initial velocity right here is 0. The other thing, what I did here is I moved the initial position over to the left side here. So what we're actually solving for here is a displacement, the final position minus the initial position. And that is equal to minus 1/2 g times delta t squared. So again, g is 9.8, and we're going to plug in for delta t. The time we were interested in was 2 seconds, how far it falls in 2 seconds. So we're going to take 2 seconds and square it there. Okay, so again, what we're really solving for here is a displacement, delta y, which is defined by y final minus y initial. So by doing the math here, you'll find that delta y is equal to negative 19.6 meters. And again, this minus sign reminds us that the object is falling downwards. The displacement is in the negative y direction. Let's now look at another free fall problem. This one is a little more difficult. Let's say you're standing on the edge of a 100-meter tall cliff, and you throw a rock upwards at 10 meters per second. The rock comes back down, just misses the cliff edge, falling to the bottom of the cliff. Okay, so here's the picture of the situation. Here you are standing up on top of the cliff. You throw the rock upwards at 10 meters per second. The rock comes to a peak, all right? We're going to call that Y max. That's the maximum height of the rock. And then the rock stops and starts falling back down and ends up down here at the bottom of the cliff. So again, we're going to ask three questions here. Part A, what is the maximum height the rock reaches? In other words, what is the value of y max here compared to the base of the cliff down here? Part B, how long does it take the rock to hit the ground? And part C, how fast is the rock going when it hits the ground? So let's go ahead and do these three problems in order again. As we talked about before, in physics, as they say, there's always more than one way to skin a cat. I know it's kind of a horrible quote there because I do happen to like cats. But anyway, you know what that means. There's often multiple approaches to problems. And so we're going to see, I believe, in all three of these parts, there's going to be two different ways we can solve for what we're trying to find. So the part A was, what is the maximum height of the rock? I'm going to show you the shortest, most efficient method here, which is in the yellow box. There's another method over here which can be used as well. But let's look at the shorter method first. So we don't have any information yet about time. We haven't solved for any times. So let's use our equation that doesn't involve time. This is the one that says v final squared equals v initial squared minus 2g delta y. We know that when the rock gets to the very top, when it's right before it starts to fall down, its final velocity is 0. And this is always the case. Whenever you throw something up in the air, it stops at some point before it starts falling back down. So we're going to take our final velocity of the rock for this part of the problem to be 0. The initial velocity of the rock we were told that the guy threw it upwards at 10 meters per second. And we have to remember to square that. So that 10 is actually going to become 100. And then we have minus 2 times 9.8, which is g, times delta y. Now we can solve this for delta y to figure out what is the displacement of the rock during this portion of the problem. So delta y is equal to 10 squared over 2 times 9.8, and that turns out to be 5.1 meters. But of course, remember, this is 5.1 meters is the displacement from where you threw the rock. In other words, the rock goes up 5.1 meters from the top of the cliff. So the maximum height of the rock is the height of the cliff, which is 100 meters, plus the distance that you threw it upwards, 5.1, and therefore the y max is equal to 105.1. So part B of this problem was to find the time for the rock to reach the ground. So in other words, the guy throws it up here, it reaches y max, remember that was at 105.1 meters, and then the rock falls from there all the way down to the ground. We want to know how long this whole process took. So again, there are a couple ways to solve this. I'm going to show you this way on this slide here first. So for this one, we're going to use the position formula. Here it is in all its glory, right? All these terms. And let's fill in the numbers that we know. Well, the rock ends up down at the bottom on the ground, so its final position y is 0. The rock we know started at the top of the cliff right here at 100 meters, so y initial is 100. We know that the initial velocity of the rock was 10 meters per second. Remember, the guy threw it upwards at 10 meters per second. Now, of course, we don't know what delta t is. That's what we're trying to solve for. This last term, 1/2 times g is 9.8. And again, our unknown is delta t, which is squared here. All right, so let's just clean this up a little bit. So I've got 0 equals 100 plus 10 times delta t minus, now 1/2 times 9.8 is 4.9. And then we have delta t squared. What I'm going to do here is notice that we can't just solve for delta t because delta t is squared over here and it's not squared here. This is a quadratic equation. So let's put this in a form where we can solve this equation. So if we multiply every term by -1, all right, all terms by -1, and we'll rearrange the equation to look like this. 4.9 times delta t squared minus 10 delta t minus 100 equals 0. Well, this is just a standard quadratic equation. remember the quadratic formula from math class. If you have something like ax squared plus bx plus c equals 0, then the solution to this problem is given by the quadratic formula, which says that x is equal to opposite of b plus or minus root b squared minus 4ac all over 2a. So what we have to do here is we have our numbers. A is 4.9, B is negative 10, and C is negative 100. So I've gone ahead and plugged all those values here into this quadratic formula here. All right, I won't read all the numbers to you. You can look at those yourself. And what we end up with here is, remember the quadratic formula, because this is a second order equation because of that x squared, there are actually two roots or two answers. So that's why there's a plus and a minus inside this formula. So here are our two answers. When written out, we get an answer of positive 5.65 seconds and negative 3.61 seconds. Well, obviously, we're going to throw out the negative time solution because that doesn't have a physical meaning in this problem, and we're going to choose the positive answer, which is 5.65 seconds. As I mentioned on the last slide, there are actually two ways to solve part B of this problem. I'm not going to go through the second method here, but the details are shown and the explanation are shown here. If you want to do this on your own, that would be great to see another method of solving for the time to reach the ground. And of course, we know it's correct because we end up getting the same answer here. Let's move on to part C of this problem. So for part C, once again, there are two alternate methods to solve this problem. I'm going to go ahead and use the second method down here. So part C, the question was, how fast is the rock going when it hits the ground? So remember, our guy here throws the rock up, reaches this maximum height, and then the rock falls and smashes into the ground. We want to know how fast it's going when it hits down here. So look at the second method here. We're going to use, again, this equation that does not involve time, all right? Because the other method, we have to know the individual times for the rock to get to the peak and then to fall down. So instead, let's use this equation here without time in it. So we have the final velocity squared is equal to the initial velocity squared minus 2g delta y. All right, so we're trying to solve for v final here. That's our unknown. We know the initial velocity is 10 meters per second. We have to remember to square that. Minus 2 times g again is 9.8. And delta y, remember, that's how far the rock falls. It starts here at 100. It goes up and it ends up down here. But the total displacement of the rock, delta y, even though it goes up and then back down, the important thing with, remember, a displacement is where it starts and where it finishes. So it finishes at 0 and it started at 100. So the displacement is just negative 100 meters. We don't care how high it went to calculate the displacement. So 2 times 9.8 times 100 is 2060. Remember, though, that's the square of the answer. So we have to take the square root of 2060 to get our answer. And that answer is 45.4. As I explained earlier, whenever you take a square root, you'll always have a plus or minus. In other words, there are two choices mathematically. But since the rock we know is falling, we will choose the negative answer. And so our final answer is negative 45.4 meters per second.